I welcome all of you. Uh, Myself Mohit Bansal, and in this topic we will discuss the concepts of heat conduction through a composite wall. And I am an assistant professor in the Department of Mechanical Engineering in ABES Engineering College. So, by this uh, numerical, we will learn the concepts of series and parallel one-dimensional heat transfer and electrical analogy. So this is the problem in which we have taken a problem. So, so first of all, this is the problem. So on the left side face of this block, the temperature is 400 degrees Celsius, and on the right side, the temperature is 60 degrees Celsius. The thickness, and this block is made up of four different materials. Material A is having a thermal conductivity of 150 watt per meter degree Celsius. Likewise, material B, material C, and material D, which are having different thicknesses, like 3 centimeter for A. B and C, both the materials are having thermal conductive thickness of 8 centimeter, and D is having the thickness of 5 centimeter, and the width of the block is equal, and that is 10 centimeter. So in this problem, what we have to find out, we have to find out the heat flow rate, that is represented by Q dot. So we have to find out this Q dot, which is flowing in one dimensional in this direction. So while solving this problem, we have to consider a few assumptions, like the one dimensional heat transfer. So we are considering that in the other two directions, no heat transfer is happening. So this is the first and foremost thing in this while solving this problem. And the temperature is constant on a face. So when we are saying 400 degrees Celsius, so the temperature is same everywhere. Likewise, on this side, right side of the portion D, that is showing 60 degrees Celsius. So everywhere the temperature is 60 degree Celsius. We have to find out Q. So this will be our first assumption, one dimensional heat transfer, and we are considering the problem as a steady state. And the third assumption we are taking, there is no internal heat generation. No internal heat generation. So we are proceeding. So these are the thermal conductivities. So this is the concept of series and parallel one-dimensional heat transfer through a composite wall and the electrical analog. So first of all, we will make a thermal circuit for the problem. Thermal circuit. So if we see the problem, so it is portion A, this is portion B, C, and D. And these are having different thicknesses. So for the first portion, the thickness is 3 centimeter. This one is having 8 centimeter, and this is 5 centimeter. This is the height, and this is total it is 10 centimeter, and here it is divided into two portions. Like this section B is having the height of 3 centimeter, and this section C is having 7 centimeter, and in total it is 10 centimeter. So this is the diagram. I have taken the front view, and we have prepared this portion. Now we will make a thermal circuit for the problem. So if we take, this is the section A, we'll make a thermal resistance for A, or thermal A. Then the B and C will be in parallel, so that will be R thermal B. This is R thermal C, and then again this will form R thermal resistance for section D, and we're having temperatures. This is, we are considering the temperature T1 at this point. The temperature at this point is T2, temperature T3, and there will be temperature T4. So in our problem, temperature T1 is showing like 400 degrees Celsius, and on the right side face of this, it is the temperature 60 degrees Celsius. And we all know that the thermal circuit is exactly, or I mean, analogous to the electrical circuit. So we all know that V is equal to IR. So in our thermal circuits, we consider this potential difference analogous to the temperature gradient or temperature difference, and this current is analogous to the rate of heat transfer Q dot, and where in the electrical circuit this R resistance signifies the electrical resistance. Now here it is analogous with the thermal resistance. So these all quantities are analogous with the electrical circuits. Potential difference is analogous to the temperature difference. Current is analogous with the rate of heat flow, rate of heat transfer, and our electrical resistance is analogous with the thermal resistance. So by considering this, we will consider and we will find out the Q dot. So that rate of heat transfer will be equal to the temperature gradient, temperature difference upon thermal resistance. This we can write as thermal resistance. Thermal resistance, where it is the temperature gradient, temperature gradient, temperature gradient. So this will help us a lot in solving the problems of composite wall, wherever the series and parallel resistances, thermal resistances will be there. And one more formula which we know for the conduction heat transfer, that is the Fourier's law of heat transfer. That Fourier's law of heat transfer is Q dot, and it is given as minus Ka, where this area is the cross-sectional area perpendicular to the direction of heat flow, minus Ka dt over dx, which we generally write as delta T over R thermal resistance. So this negative sign shows the direction of heat flow. K is the thermal conductivity of the material. ACS shows the cross-sectional area. This dt is the temperature gradient, and dx shows the thickness. So by considering these two facts, we will solve our problem and find out the rate of heat flow for this circuit. So first of all, we will calculate the resistance, individual thermal resistances for A, for B, for C, and likewise for D. So first of all, we will take the thermal resistance for material A. So it is L over Ka for material. If it is for material A, so we will write it as this thermal conductivity of material A into the cross-sectional area of A. Okay. Likewise, for thermal resistance for B, LB over KB into AB. Thermal resistance for material C, LC, here it will be LA, and it will be KC into ACS for material C. And the last one, thermal resistance for the section D, we will take the length or thickness of section D, and in the denominator it will be thermal conductivity of D into the area of the section D. So first of all, we will calculate the individual thermal resistances. So for this LA, we will take the thickness of this section A, which is made up of a material of thermal conductivity, which is shown as Ka. So we will write as La as 3 centimeter. So it will be 0.03. We'll take dimensions in meter. And thermal conductivity of material A is 150 watt per meter degree Celsius. 150. And now the thing is cross-sectional area. Now if we see the area which we take in the Fourier's law of heat conduction, it is the area which is perpendicular to the direction of heat flow. So if the direction of heat flow is this, and we are considering the unidirectional or one-dimensional heat flow, so the area which is perpendicular to the direction of heat flow. So if the heat is flowing in this direction, x direction, the area considered will be this one. So area will be this 10 centimeter into this height, and this total height is 10 centimeter. So 10 centimeter into 10 centimeter, that will be the area of the face or perpendicular to the direction of heat flow. So that will be, if it is 10 centimeters, so that will be 0.1 into 0.1. So here we will write the thermal resistance for A. Now we will write it for B and C. The thickness for both the B and C is same, 8 centimeter, and the area will be different because the perpendicular area for the direction of heat flow, that will be for this section B, it will be 10 centimeter, 10 centimeter into the height, this 3 centimeter for section B, and 10 centimeter into this height, that is 7 centimeter, that will be the cross sectional area for C. So 10 into 3 and 10 into 8 respectively for B and C. So 8 centimeter will be the thickness. So it will be 0.08 into thermal conductivity of B, that will be 30 into 0.1, 0.1 into 0.3. For C, the thickness will be same, 0.08 upon the thermal conductivity is 65 watt per meter degree Celsius into cross-sectional area of section C. So that will be 0.1 into the height 0.7. And now for section D, it will be 0.05 upon the thermal conductivity of section D, that is 50, into the cross-sectional area of D. The cross-sectional area will be height of the section, that is 10 centimeter, and this 10 centimeter. So it will be same as that of a 0.1 into 0.1. So the values which comes out to be, after solving the thermal resistance for section A, B, C, and D, we will take it as the thermal resistance for section A comes out to be 0.02. For section B, it comes out to be 0.89. For section C, it comes out to be 0.176. And when we will solve for thermal resistance of section D, it comes out to be 0.1. So now we have calculated the thermal resistances individually for A, B, C, and D. Now we will see in this network diagram that B and C are in parallel. So we have to calculate the equivalent thermal resistance for B and C. And as we have said that this is analogous with the electrical circuits, so we will calculate the equivalent. I am changing, just a second. Yes. So now we will calculate the equivalent thermal resistance, for B, C. So that will be equal to, we all know, so I'll write it here, 1 upon R equivalent for B and C equivalent will be equal to 1 upon the thermal resistance of B plus 1 upon thermal resistance of section C. So when we will solve it, R equivalent for section B and C comes out to be thermal resistance for B into, just a second, into thermal resistance for section C upon R thermal B plus R thermal resistance for section C. So on solving, this equivalent resistance for section B and C comes out to be, on solving, this comes out to be 0.147. You can check it later. You can calculate it, thermal resistance. So by this, what we have done, we have simplified our electrical resistance of this parallel network, and now our complete network diagram becomes thermal resistance for A, thermal equivalent resistance, thermal equivalent resistance for section B and C, and this will be thermal resistance for section D. So we have all the values with us. This is temperature T1. This is, we have considered as temperature T4. This is temperature. Although in this problem, we are not considering the temperatures T2 and T3. But yes, in the next problem, we do calculate the temperatures, intermediate temperatures between the resistances of our thermal resistance of A and equivalent thermal resistance of B and C. We can calculate T2 as well as T3 very easily. So this is the direction of heat flow Q dot. Now these three resistance are in series, so that will be very much easier to calculate the cumulative thermal resistance for this in a single equation. That will be just the summation of thermal resistance of A, thermal resistance of section B and C, and thermal resistance of D. So in totality, we just add these thermal resistance of like A 0.02, which was 0.02, plus the equivalent resistance of B and C, which comes out to be 0.147, and the thermal resistance of section D, which is 0.1. So it comes out to be 0.267. 0.267. So what we have done, we have just simplified our network in a single resistance where each of the resistance is in series and they are calculated. So it comes out to be 0.267. Now it will be very much easy to calculate the this rate of heat flow, because we have discussed this thing here, that the rate of heat flow is equal to the temperature gradient to the thermal resistance. So we have calculated the combination of series and parallel resistances. So we will just write it up like delta T upon the thermal resistance. So delta T will be 400 on the left side, 400 degrees Celsius minus 60 degrees Celsius upon the thermal resistance, that is 0.267, and it will be 340 upon 0.267. It comes out to be 1273.4 watt. So our final rate of heat flow in this problem comes out to be 1273.4 watts. So this is the final answer of our problem. In addition to this, we can calculate the temperatures like T2, T and T3 in the same manner. And if someone wants to check whether we are moving in the right direction or not, whether we have taken the right procedure or right, our values are correct, so we can calculate the temperatures of T4. So if T4, if we are moving in the right way, so T4 will automatically comes out to be 60 degrees Celsius. So we know we can, uh, take this relation and apply in between this thermal resistance of A. So if someone wants to calculate, then you may also try, because in this series the rate of heat flow or Q dot will remain the same. So by using this like electric, as we know, heat flow is just analogous to the current. So in this series the current remains the same, and in parallel it divides. So these resistances we will consider it in, they are in series. So we will take this Q dot as like uh, T1 minus T2 upon R thermal resistance for A. Likewise, this will be equal to T2 minus T3 upon thermal resistance for equivalent thermal resistance for section BC, which comes out, which was coming as 0.267, and this is also equal to the T3 minus T4 upon the thermal resistance for section D. So by this relation, we have the rate of heat flow as 1273.4 watts. So on the left side, we will pick one equation out of these three, and we will put the value of heat, rate of heat flow as 1273.4 equal to, we do have T1, we don't have this T2. So by this relation, we can easily find out the unknown temperature as T2, which is there, just see here, which is lying in this section. Okay, and in the same manner, if we have T2, by putting this rate of heat flow, we can calculate T3 from this relation, second relation. And if we are moving in the right manner, just put the value of T3, you will see that T4 will automatically comes out to be 60 degrees Celsius. So I am telling you the values of T2 and T3. If you will calculate the uh, same in the same manner, so T2 comes out to be, it comes out to be 374.53 degrees Celsius. T3 comes out to be 187.34, and T4, you just calculate it. It will help you in understanding the concept. So in this problem, although the temperatures were not in the scope of this problem, but yes, we can calculate very much easily the temperatures intermediate between any two, I mean, like A, B, which the connections were in series and in parallel. We can calculate the temperatures in between very easily by using the same equation. So what we have learned in this problem, we have learned in this problem that the uh, thermal circuits are analogous with the electrical circuits. The potential difference is analogous with the temperature difference or temperature gradient. Current is analogous with the rate of heat flow Q dot, and the electrical resistance is analogous with the thermal resistance. By using the same concept, we have taken this Fourier's law of heat conduction, Fourier's law of heat conduction. So a few assumptions are also there while deriving this Fourier's law of heat conduction, like steady state heat transfer is there, unidirectional heat conduction is there, and the material is isotropic and homogeneous, and there is no internal heat generation, uh, and the thermal conductivity or the temperature on a face is like same. There is no temperature gradient on a face, so it is same everywhere. On like if we are saying 400 degrees Celsius, so 400 means it is same everywhere. If you take any section, 400 degrees Celsius will be same everywhere. So we have learned this concept, and by using this concept, we have calculated the resistance, individual resistances, and then the equivalent resistance of section B and C, because both of them were in parallel, and then they form the series network. So you can calculate and find out the values of uh, resistances, and then we have calculated the rate of heat flow. So by this, we are ending this topic in which we have calculated the heat conduction through a composite wall. Thank you, everyone.